Hello everyone, this is Anik Tahabilder, and today I will be presenting the paper SmartSync Cross Blockchain Smart Contract Interaction and Synchronization. This paper is authored by Martin Westerkamp and Alex Cooper. The outline of the presentation: today I will be describing the problem statement and some background related to this problem. And then I will talk about the main methodology the author have proposed, which is smart contract synchronization. And then they also have provided evaluation of their method, so I will be talking about that, and finally I will finish the presentation with a conclusion. So let's talk about the problem statement. The first heading is isolated smart contract. So in nowadays, if the smart contract is deployed in any blockchain, so there is a difficulties for interacting between two smart contract. So in the image we can see that there is a blockchain A and blockchain B, and inside blockchain A two smart contracts are deployed, which is X and Y. So they can interact with each other, but when two smart contracts are deployed in two different blockchain, like smart contract Y and smart contract G, they cannot interact with each other because retrieving data between two smart contracts which are deployed in two different blockchain is very much difficult. So this is a big problem, and this is considered as lock-in effect. So a smart contract cannot be transferred or cannot retrieve data from any other smart contract deployed in another blockchain network. So this problem is called Oracle problem. This problem states that when two smart contracts are deployed in two different networks, they cannot interact with each other. They cannot read the data from each other. An example of that lock-in effect or smart contract interaction problem is the implementation of ENS, which is Ethereum name service. So this service provides name of wallet address, but this service is limited in the Ethereum network because this is a smart contract implementation, and that smart contract must be unique and it cannot be copied to other network. As a result, this naming service works only when the network is in Ethereum. So this is an example of the problem in interacting two smart contracts which are deployed on different network. And DeFi is another most popular application in public domain for blockchain. So DeFi is used to automate the market makers, and they helps to provide some information for different trading of assets. But in order to use that facilities, our smart contract need to be deployed on the same network. For example, if the DeFi smart contract is in Ethereum blockchain, we need to deploy our smart contract also in Ethereum, even though if it is not most suited. For example, Avalanche network may be good for high speed transactions, but in that case the smart contract cannot communicate with each other. So the goal of this paper is to provide cross chain access so that the information can be retrieved over the blockchain boundaries. So here is a summary of the contribution of this paper. So this research paper actually implement the synchronization of smart contract. For example, here is a blockchain A and this is a blockchain B. This blockchain has a logic and a state, and we can see that the logic and state has been transferred, and when the state is updated, that will also be synchronized as shown in this image. So this process is done with a smart contract synchronization procedure, so which creates a smart contract fork, and then it distributes across the blockchain network, And then the synchronization state is must be trustless and lightweight, and also a transaction confirmation procedure has been used, and eventually the implementation of this method has been verified, and all the resources has been provided in a public repository for verification or for public use. So in order to implement the trustless environment, they have introduced three concepts, which is chain relays and sharding and notary schemes. So chain relay is usually producing a light client of the source blockchain on the target blockchain. So this is typically executed in the smart contract, and we don't need any trust in relayer, or we also don't need any collateralization. And sharding is another procedure where multiple blockchains are executed in parallel based on a shared consensus. Notary is a different procedure where one or many validators signs estate transactions or events. So it often includes threshold signatures in the notary schemes procedure. So smart contract interaction needs a common execution environment. Here we know there are a lot of popular smart contract or blockchain network execution environment, including the Avalanche, Ethereum, or Hyperledger Bureau. There are a lot of variations among the network, so including some public and private. And also there is difference in the consensus protocol that includes proof of work, proof of stake, and also practical Byzantine fault tolerance. And for the common execution environment, this paper has used the Ethereum virtual machine EVM, and the smart contract is deployed in that Ethereum virtual machine execution environment. So in order to implement the methodology of interaction between two smart contracts, so the author has claimed that there should be some prerequisite, and they have mentioned four important point here. So that includes equality, completeness, succession, and trustlessness. So equality implies that a state of secondary contract must reflect a state of primary contract, and completeness means the entire state must be captured during the initialization. A partial set or a subset cannot be executed itself. And the succession means after the synchronization, the state must be at least one more than the previously applied state. And trustlessness ensures that the correctness must not be dependent on a third party. So the very first step of this smart contract synchronization is the initialization of a smart contract fork, and this procedure is completed in several steps. So the first of all, the smart contract is retrieved from the client, and after that this is deployed, and there is a validation step. So the smart contract is retrieved from the client, and that includes both logic and state. So in order to retrieve the state, sometimes there is a naive approach, or mostly the FATDB client nodes process is applied, which is much more efficient. And when both the logic and the state is retrieved, then it is deployed in the target. And for the deployment, we also use the different function, because this proxy contact which is being used for deployment, this will break down the procedure into several steps so that the gas limit is not exceeded. So first step of deployment is the logical contract, and then the proxy contract will be deployed, and this proxy contract will register itself, and it will set a pair of key values to set the states as many times as needed, and then there will be a verify function to match the source and the target blocks. So when they are equal or equivalent, then this procedure is finished, and then any entity like Bob can call for a get function to make any transaction, and that will go through the proxy contract, and this proxy contract will then call the logic, and whatever value is retrieved, that will return to Bob. And eventually there is a validation is a step, and the validation is completed using chain relay. And here is the naive approach for replaying the transaction. So in the figure we can see in the blockchain there is a smart contract, and here is the fork of that smart contract in blockchain B, and 3 transactions have been taken place in blockchain A, and they need to be somehow copied in the blockchain B. So there are some problems, like this is the overhead because each of the transactions need to be copied, but there is a problem with that. Copying all these transactions is not necessary. For example, in transaction on the state was 6, and then it in transaction 2 it becomes 7, and then it again comes back to 6. So even if we don't make any modification, that was also good. Also in this procedure, the resulting state cannot be subsumed. As a result, the efficient chain relay procedure like GK relay cannot be used. Besides, the account in blockchain B can be in a different state, so mimicking all these transactions is not good idea, because the account may not have sufficient funds for that, the gas price. So that are some problems in naive approach for this execution of the block in a new blockchain network. So here the author have used a very new approach, which is a verifiable state updates approach. So here we can see that instead of depending of all the transactions that took place, they only consider that the final states, which is the transaction 3, and they just consider that this state is existing. So this is the last step, and this is definitely existing, so they start putting this state first in the other blockchain like blockchain B, and this procedure is done in 2 steps. One is state retrieval and another is state update. So for the state retrieval, state difference is created, and then a key value pair reflects the update, and then the values are added or deleted. And state updates are done using 2 procedures. One is account proof and another is storage proof. So they works on 2 different mechanisms. For example, this storage proof works based on key value pair in the smart contract state. But implementing this step, only 3 conditions are met, which is equality, succession and trust. But there is a 4th condition, which is completeness, that is not yet confirmed. So here is the transaction confirmation procedure. So here we can see a Merkle tree, and the tree root state is A, and we can see the key value pair in the leaf node, and in the H node and I node we can see it has been deleted in the right side image here, and the node H has been modified in S here, and a new node has been added, the T node, which has been differentiated by putting color. So instead of doing a single verification for each operation, they have introduced a multi-proof. So multi-proof makes the computation efficient. but it cannot guarantee the completeness state as mentioned earlier. So we can see that the left Merkle tree is of an account state derived from source chain, and the center on which is multi-proof of an updated state where this is deleted and this key is modified and this key is added. However, in the right side, that is the transaction confirmation, which is calculated on the target chain, and this is equivalent to the first step. So this gives us the Merkle proof or completeness because they are equivalent. We can see here even the root state and everything is equivalent. So this is the transaction confirmation procedure. So in our earlier proof, we have seen how multi-proof permits the proof by providing multiple key value pairs, and then the transaction confirmation procedure confirms that there is no state withholdings after the synchronization. And here is a block diagram of the procedure. Let's see how it works. So the smart contract get account proof, and when that data is retrieved, then they get the transaction proof, and then all these are replied, copied in the target blockchain, and then it gets the storage proof key, and taking that it creates a optimized Merkle proof, which is complete Merkle proof. And after that, the account proof and storage proof is verified. When the verification is done, the multi-proof is procedure also take place, and it also creates the transaction confirmation and then verify the transaction confirmation. And when each of the state is verified, then the state is updated. And so that is the working procedure of the synchronization of this SmartSync method. The author have also provided a client and smart contract to mimic this procedure, and the client includes the replace of transactions using source blockchain node, and also can create the state differences, and that can also create multi-proof and also submit the proof to the target contract. And for the smart contract side, it can create mapping between primary and secondary contract, and it can track synchronization state. It can forward logic execution using the proxy, and it can also verify the state update using any of this method that includes multi-proof, account proof, or transaction confirmation. So all these resources is available in this GitHub repository. For the evolution of the proposed model, the author have explained two different evolution. One is for single value update, one is for multiple value update. And for single value update, they have two parameters to consider: the execution cost and the latency. So in the left side from the figure, we can see that, so if the storage is 10, then the Merkle height it lies between 2 and 3. So when the storage get increased, the depth of the Merkle tree also increased, and with the increase of the Merkle tree depth, the gas cost also increased. From the figure we can see that. The summary of this is, with the increasing the length of the blockchain, so the summary of transaction keep getting increased. And for the latency, they have reported that the transaction time was 90 to 475 milliseconds depending on the depth of the Merkle tree. So for the multiple value update, in a similar way, the execution cost increases when the storage size get bigger. For example, if the storage size is 100, we can see this line, but when the storage get increased into 1000, we can see this line is growing faster. So the gas used is growing faster. And for multiple value update, we can see the latency time is for 10 values, it is 120 millisecond, and for 1000 value, it is 1897 millisecond. So in conclusion, so in this paper, the authors has proposed and provided a cross-chain smart contract synchronization procedure, and a prototype has also been provided, which is open source and available in GitHub. And they have also made evaluation of the procedure and reported the parameters, I mean the performance of the proposed model. And they have also explained two use cases, including the DeFi and Ethereum name services. And that's all. Thank you so much for watching.